In this video, we will practice finding the area bounded by two or more functions, and we will practice finding the volume of a solid sitting on an area bounded by two or more functions. Problem number 6. The shaded region is bounded by these three graphs. Set up and evaluate an integral expression to find the area of the region. You can find the area of the shaded region by integrating with respect to x if you integrate the top function minus the bottom function. From left to right, the shaded region goes from -1 to +1, so these are the limits of integration. In this case, the top function is the blue function, 4 over 1 plus x squared. The bottom function is the red function, 1 minus x. So here we have the top function minus the bottom function. On the next step, I will distribute the negative sign across the parentheses. Don't forget about the inverse trig rules that we learned back in Unit 7. This first term is a perfect match for the arctangent rule with an a value of 1. This 4 in the numerator means that we have an extra multiple of 4 that we will end up sticking out in the front. So the antiderivative of this is just going to be arctangent of x. Except don't forget about the 4 in the front. Moving on to the next term, the antiderivative of 1 is just x. Moving on to the x term, we will increase the exponent and make it x squared, but then we have to divide by this new exponent, so I put a 1/2 in the front. Now we will apply the limits of integration from -1 to +1. This means we need to find the value at +1 minus the value at -1. So here is the value at 1 minus the value at -1. To evaluate the arctangent of 1, you should be asking yourself the tangent of what angle is equal to 1. In the first quadrant, the tangent of pi over 4 is equal to 1, so that is the value of arctangent 1. I'm always keeping in mind the restrictions on inverse trig functions. For example, arctangent is only defined between -pi over 2 and +pi over 2. So that's up into the first quadrant and dropping down into the fourth quadrant. So for any positive value, I'm going to use the first quadrant. For a negative value, I will move clockwise down into the fourth quadrant. When we look at the arctangent of -1, we ask ourselves the tangent of what angle is equal to -1. Well, arctangent is only negative in the fourth quadrant, so that's going to be -pi over 4. Evaluating the inverse trig functions and applying the exponents, we have this. If we do all of the multiplication, we get this. On the next step, I will distribute this negative sign and take away the brackets. Pi plus pi is 2pi. -1 and -1 make -2. 1/2 and -1/2 cancel each other out. So the area of the shaded region is 2pi minus 2. Number 7. The region A is bounded by y equals cosine x and y equals 0 for the closed interval from 0 to pi over 6. A is the base of a solid for which cross-sections taken perpendicular to the x-axis are semicircles. Set up and evaluate an integral expression to find the volume of the solid. The integral expression turns out to be one that we can't evaluate without a calculator, so that's why they have it crossed out, and we won't be trying to evaluate. We'll just set it up. As we prepare to sketch the region, let's first remember what the parent function y equals cosine x looks like. So from 0 to pi over 6, we're talking about a very small portion of this cosine function. So we're just talking about the very beginning where it's just starting to head downward. That's all we're graphing. We are given this domain from 0 to pi over 6, and that forms part of the boundary of the region. Other than that, region A is bounded by y equals cosine x on the top and y equals 0 on the bottom. This is a problem where we are trying to calculate the volume of a three-dimensional solid. So when I mention a solid, I want you to picture a loaf of some strange bread that's sitting on this yellow footprint, and we're looking at it from above. When they talk about cross-sections taken perpendicular to the x-axis, they are talking about slices like this. And we will use slices like this to calculate the volume because we will add up a bunch of slices by integration, and together those slices will form the volume. There are 3 steps to finding the volume of a solid. Step 1 is to write an expression for the length of the base of a single slice. And then step 2 is to write an expression for the area of a single slice. And then step 3 is to add up all of the slices by taking the integral. So step 1 is to find an expression for the length of the base of a single slice. That's the length of this purple segment. So we can just do the top function minus the bottom function, which will be cosine x minus 0. And of course we don't really need the 0, so in this case the base is simply cosine x. And that's the end of step 1. Step 2 is to come up with an expression for the area of a single slice. In this case, we are told that the slices are semicircles. So each slice is a semicircle with base b, and we need to come up with an expression for the area of this in terms of b. I'm about to show you the 6 most common shapes of slices with base b and an expression for the area of each one. Some of these are really obvious, like if you have a slice in the shape of a square, if the base of the square is b, then the area will be b squared. Some of them take quite a bit of work to come up with these formulas. My suggestion to you is to pause the screen and write these formulas into your notes and memorize them. That way you don't have to come up with them in the middle of a test problem. So here are the first 4, and here are the last 2. Pause the screen, copy these down, and memorize them. You will thank me later. For this particular problem, we needed an expression for the area of a semicircle with base b. And here it is, pi over 8 b squared. Okay, so the area of a single slice is pi over 8 b squared. I want to take the expression that we have, the expression for the base, and I want to modify it to turn it into an expression for the area of a single slice. Since the area is pi over 8 times b squared, and this is b, then to make this into area, I need to put a pi over 8 in the front, and I need to square it. Now it's pi over 8 b squared. This is an expression for the area, and that's the end of step 2. Before we go on, someone might want to see where this expression pi over 8 b squared is coming from, so I will quickly run through it. We know that the area of a whole circle is pi r squared. So right away, if we are talking about a semicircle, then that would be 1/2 pi r squared. R stands for the radius, but what we have here is the diameter. So if I want the radius, the radius is going to be half of b. So my expression for the area becomes 1/2 pi, and instead of r, the radius is half of b, so I'm going to put 1/2 b. If I square 1/2, I get 1/4. So squaring this expression inside of the parentheses, I get 1/4 b squared. We still have this 1/2 pi in front of it. Let's multiply these together. 1/2 times 1/4 is 1/8. So we have 1/8, and then we still have the pi, which I can stick on the top. So all of this together makes pi over 8, and then we have b squared. So that's where the little formula came from. By the way, if you take my advice and you try to memorize these formulas, notice that almost all of them involve b squared. Starting with the area of a square with base b, that is b squared itself. And of course, if you do an isosceles right triangle that is sideways, then of course that is just half of a square, so it's half of b squared. If you take your isosceles right triangle and put it hypotenuse down, maybe you can see that 4 of these will fit inside of a square. So that's why this is 1/4 b squared. So looking at these patterns, it will help you to memorize these formulas. Except for the rectangle, they all have b squared in it. It's just 1/2 b squared, 1/4 b squared. For the equilateral triangle, it's radical 3/4 b squared. And then for the semicircle, it's pi over 8 b squared. So if you know that they all have a b squared in it, except for the rectangle, then you've already memorized half the formula. You just have to memorize the coefficients. Anyway, the third step is to find an expression for the volume by integrating the area. When you integrate the area, you are adding up a bunch of slices. And when you take a bunch of slices together, you have the volume of the solid. So I can turn this expression for area into a volume by integrating it. I am integrating from 0 to pi over 6. So these are the limits of integration, 0 and pi over 6. As far as the setup goes, this is it. This is the expression for the volume of the solid that is sitting on this yellow area. I would probably just modify one small thing. Instead of writing cosine x squared with parentheses like this, we should write cosine squared x. The regions R, S, and T are in the first quadrant, bounded by the axes and the graphs of y equals 16 minus x squared, y equals 3x squared, and y equals 6x. Write, but do not evaluate, integral expressions to represent each area or volume. Number 8. Write the area of R written with respect to x. When you find the area by integrating with respect to x, you can integrate the top function minus the bottom function. In this case, the top function is 16 minus x squared, and the bottom function is 6x. In order to write the limits of integration, we need to know what the intersection point is between these two curves. So let's set them equal to each other and solve. So we have 6x equals 16 minus x squared. Let's add x squared to both sides and subtract 16 from both sides. In other words, let's move both of these things over to the left. Then we will have x squared plus 6x minus 16 is equal to 0. This is probably factorable, so let's give that a try. X squared can only factor as x times x. 16 could be 4 times 4, but in this case it will factor as 2 times 8. To come up with a middle term of positive 6x, we need a -2 and a +8. Using the zero product property, we get x equals 2 and x equals -8. The second one is not in the first quadrant, so it does not apply. The x equals 2 gives us the x-coordinate of this intersection point. So we know the intersection point is 2 comma something. To get the y-coordinate, we can just use the fact that y is equal to 6x. That's 6 times 2, which is 12. So from left to right, the limits of integration will be from 0 to 2. So that's it. This is an expression for the area of R, written with respect to x. Number 9. Find the area of R written with respect to y. If you want to find an area by integrating with respect to y, you integrate the right function minus the left function. However, in this case, that's going to be a bit of a problem because we actually have two different functions on the right, depending on how high you are. Below a y value of 12, on the right-hand side, we have the purple function 6x. But above 12, on the right-hand side, we have the red function 16 minus x squared. Since we have two different functions on the right, we have to write two different integrals. Also, since we are integrating with respect to y, we need to rewrite both of these functions in terms of y. So let's solve for x. Adding x squared to both sides and subtracting y from both sides, we get x squared is equal to 16 minus y. Taking the square root of both sides, we get x is equal to the square root of 16 minus y. So this is the version that we will use for this problem. Normally I would say plus or minus, but we're in the first quadrant, so only plus. We can easily solve y equals 6x for x by dividing both sides by 6. We just get x is equal to y over 6. And this is the version that we will use for this problem. So first we will integrate from 0 up to a height of 12. So 0 to 12, and as we integrate, we will integrate the right function minus the left function. So this will be y over 6 minus 0. So here's the first integral. Of course, we don't really need the minus 0 part, so I'm going to erase that. Now let's add the next integral. This time, we will pick up where we left off, and we will integrate from 12 up to the top of this parabola. I can tell that this is at a height of 16, because 16 minus x squared is an upside down parabola with vertex at 16. So for the second integral, we will integrate from 12 to 16. We will integrate the right function minus the left function. So the square root of 16 minus y minus 0. And again, we don't really need the minus 0 part. So here is the final answer for number 9. For problem number 10, let's find the area of T written with respect to either x or y, our choice. T is bounded by 3x squared on the left and 16 minus x squared on the right. I am going to integrate with respect to x because that's what I'm most comfortable with. When we do that, we have to integrate the top function minus the bottom function. I will need two different integrals because I have two different top functions as I move from left to right. Also, I need to figure out what the x value of this intersection point is. This is where the equation y equals 16 minus x squared hits the x-axis. this is where this equation is equal to 0. So let's just set this equal to 0 and solve. I have 16 minus x squared. Where does this equal 0? Well, adding x squared to both sides, we have 16 is equal to x squared. Taking the square root of both sides, we have x is equal to 4. Normally I would say plus or minus 4, but we're in the first quadrant, so I'm just going to say 4. Now I'm ready to set up my integral. First, I will integrate using the green function as the top function and 0 as the bottom function. So I'm going to integrate from 0 to 2. Remember that 2 is the x-coordinate of this intersection point. So I will integrate from 0 to 2, and I will do 3x squared minus 0, top minus bottom. I don't really need to write the minus 0, so this is the first integral. Now let's add the second integral. Picking up where we left off, we will integrate from 2 over to 4. Doing the top function minus the bottom function will be 16 minus x squared minus 0. So here's the answer to number 10. Finally, for number 11, we will find the volume of a solid whose base is region S, and cross-sections taken perpendicular to the x-axis are equilateral triangles. There are 3 steps to finding the volume of a solid. First, you find an expression for the base of a single slice. Then, you find an expression for the area of a single slice. Finally, you find the volume by integrating the area. Region S is bounded by 6x and 3x squared. Picture a skinny little loaf of bread sitting on this region, and we are looking down on it from above. We need to find the volume of that solid. Step 1 is to find an expression for the base of a single slice. So this little red segment, picture it as the base of one slice. How long is this segment? Well, that's going to be the top function minus the bottom function. So in this case, that will be 6x minus 3x squared. So that's step 1. We have an expression for the base. Step 2 is to find an expression for the area of a single slice. We are told that the slices are equilateral triangles. Now, hopefully you memorized the formula for the area of an equilateral triangle with base b. Remember, almost all of the formulas involve b squared. For an equilateral triangle, the coefficient was the square root of 3 over 4. So this is the formula for the area of an equilateral triangle with base b. Really, these are the 4 formulas that you need to memorize. The others are common sense. Pause the screen. Memorize this, man. We're still not done with step 2. We need to transform this expression for the base into an expression for the area. So I'm going to erase this b, and I'm going to put a equals, area equals. Well, area is the square root of 3 over 4 times the base squared. And this is the base. So if I want to transform this into an expression for area, I need to put the coefficient of square root of 3 over 4 in the front, and I need to square it because it is base squared. Now we have an expression for the area of a single slice, and that is step 2. Step 3 is to find the volume by integrating the area, because when we integrate the area, we are really adding all of the slices together, and that gives us volume. So all we really need are the limits of integration. Region S begins at an x value of 0 and ends at an x value of 2. So we will integrate from 0 to 2. So that's it. This is the final answer for number 11. This is an expression for the volume of the solid that is sitting on region S. Hey guys, that was actually the end of the video. But if anyone wants to see where this formula came from for the area of an equilateral triangle with base B, I'm going to show you that now. So this is an equilateral triangle and the base is B. And because it is an equilateral triangle, all of the sides are really base B. We want to find an expression for the area of this in terms of B. We know that the area of a triangle is 1/2 base times height. So the base is B, and I'm just going to temporarily put h for the height. So that height is right here, but we don't want a new variable. Somehow we need to replace this with an expression involving B. So how are we going to do that? Well, we can use the Pythagorean theorem. Let me erase this B for a second. By drawing the height, we form two right triangles. Focus on the triangle on the right-hand side. The base of this triangle is half of B. So I'm just going to put a little 1/2 B right here. So we have the height, and we have 1/2 B, and we have B. Those are the three sides of this triangle. So we could do the Pythagorean theorem right now. And it would go like this: h squared plus 1/2 B squared is equal to B squared. I'm doing leg squared plus leg squared is equal to the hypotenuse squared. So I have h squared plus, if I square 1/2, I get 1/4. So squaring this expression inside of the parentheses gives me 1/4 B squared. And that's equal to B squared. If I subtract 1/4 B squared from both sides, let me just show it. So I have h squared is equal to B squared minus 1/4 B squared. Well, B squared is like 1 B squared. These are like terms. 1 minus 1/4 is 3/4. So I'm going to have h squared is equal to 3/4 B squared. Finally, to get h, I can take the square root of both sides. So h will equal, well, if I take the square root of 3/4, I'm stuck with the square root of 3, but the square root of 4 is 2. And then the square root of B squared is just B. So this is a nice little expression for h. So getting back to our main goal over here, we want an expression for area, which is 1/2 base times height. But now we have this expression for height. So the area will be 1/2 base times the square root of 3/2 B. So if I multiply 1/2 times the square root of 3/2, I end up with the square root of 3/4. And then I have B times B, which is B squared. So that's how I got this formula for the area of an equilateral triangle with base B. But you do not want to have to go through this in the middle of a test problem, so just memorize it.